Hello, everybody. Welcome back to another lecture in the data structures and algorithms module. Today, we are going to talk about recursion, which is a very different way of thinking from what we're used so far in programming with for loops or while loops and iteration in general. A recursion is going to be very, very useful as we jump to talking about search algorithms and sorting algorithms, and we're going to also talk about how certain data structures can be recursive later in the module. So in a nutshell, today we will talk about what recursion is. We will see how we can use recursion in various problems. We are going to go and look at some examples of recursive problems in computing, traditional ones like factorial and Fibonacci numbers. As part of that, we will practice to define base cases and recursive cases in recursive code. This is going to be some new terminology we will introduce. And then we're going to see how to read and write recursive functions in Python and in C++. So let's start with what is recursion, right? It's a very, very common concept used in computer science and in computing. As I mentioned, multiple algorithms depend on recursion, multiple data structures depend on recursion. Generally, a lot of the recursive problems can be done iteratively with a for loop or a while loop, but in many cases that can be counterintuitive or can make the code not elegant and too complex. So recursion makes sense sometimes for certain algorithms and data structures, as we'll see. We say that an algorithm is recursive if it's used in its own definition. So a recursive algorithm calls itself, a recursive function or a recursive method calls itself. Recursion will make it possible for us to solve problems with very simple algorithms, and it will help us store data in unique ways. So how will we call ourselves recursively without running on forever, right? Without running out of space and memory and so on. Recursion will follow three basic steps. Any problem will have to become slightly smaller as we're working with it. So when I am trying to solve a problem recursively, in order for me to be able to stop at some point, I have to make the problem slightly smaller. And we'll see a couple of examples of this today. Once I've made the problem smaller, I'm going to go ahead and delegate the problem. The way that I delegate it is by calling the same algorithm or the same function over and over and over again, but again with a slightly smaller input. And once I receive the solved problem from the delegation, I will combine it with my remaining part of the problem and get the answer. So in a nutshell, this is how recursive functions are going to work. You make the problem slightly smaller, you delegate it, you wait, delegation brings the result back, you combine it with what's left of the problem. Let's look at how this is going to be represented when we're trying to make a cake. And this is purely a conceptual example, so we understand recursion a little bit better. Assume you are trying to build a 4-layer cake. If you had to do this cake on your own, right, and the layers are getting smaller and smaller, you're making like a fancy tower cake. You have to do the first layer, right, bake it, bring it out, do the second layer, bake it, bring it out, do the third layer, bake it, bring it out, do the fourth layer, bake it, bring it out, put everything together. So that takes quite a bit of time and effort. So let's say you don't want to do that, you're being lazy. So what you're going to do is instead decide, okay, I'm going to do one layer and one layer only. So I only turn the oven once to bake one. And then I'm going to give one of my friends to do the other 3 layers, right? So I'm making the problem slightly smaller. I do one layer myself and I give the other layers to some other friend, right? Somehow, automatically, that other friend gets me 3 layers of cake that are finished, right? So I delegate the work to my friend. They somehow automatically get me these 3 layers of cake. We will see in a second how that is going to work. But now I have a 3-layer cake that is done and my 1 layer of cake. What is left for me to do? The only thing I need to do is combine them together, right? So take the bottom layer that I created myself, take the 3 cake, put it together, and now I have a 4-layer cake. Notice how this process is very different from doing the cake yourself, right? When we were doing it with ourselves with something like iteration, so do one, bake it, put it down, do another one, bake it, put it down, do another one, right? So it feels very sequential. In this case, right, I only do one layer myself, and then I just wait for the delegation work to be done. I tell my friend, hey, here, you figure out how to do a 3-layer cake. The only thing I need from you is 3 layers. I don't care how you do it automatically, right? So once you get those 3 layers, you have your 1 layer. The only work that you do is you put it together, and then you're done. Let's look into a little bit how does the automagic part actually work out, right? So how does this delegation work automatically? Let's say that I was asked to make a 4-layer cake, right? And again, I'm being lazy, so I'm going to do a layer myself and ask my friend to do 3 layers of cake. My friend is also being kind of lazy. So what they're going to do is make 1 layer themselves and give one friend to make 2 layers, right? So the delegation keeps going on and on, right? I'm lazy, I do 1, give you 3. You're lazy, you do 1, give your friends 2. That friend is lazy, they're going to do 1, give another friend 1. And that friend that was asked the last one to make 1 layer of cake, they could just go ahead and do it, right? So this is the process of how we're making the problem smaller and delegating, smaller and delegating, smaller and delegating, right? So you're not the one that is doing all the 4 layers. You give it to a friend who does 1 and gives it to a friend who does 1 and gives it to a friend, and then 1 is done. Once we hit this particular making 1 layer of cake, I don't need to make the problem smaller, and I can't really make it smaller. I can break 1 layer of cake into half layers, right? It doesn't really make sense. So that we will call the base case. That is how we know we stop. When we reach a problem that we can solve immediately without having to make smaller and without having to delegate, that's our base case. So that friend builds the 1 layer of cake, gives it back to the friend who asked them to build the 1 layer. This friend takes that 1 layer, puts it together with their layer. Now they have a 2-layer cake and gives it back to the friend over here who was going to build 3 layers but was being lazy and just built 1 layer. That friend takes their layer and the 2 layers that the friend before gave them and gives it to me, right? And I go ahead and take the 3 layers that came to me and put my 4th layer together, and now I have the cake ready. So again, let's very quickly backtrack. I take the big problem, do a small portion of the problem myself, make it smaller, delegate it. My friend does the same, does a small portion of her problem themselves, delegate it. Their friend also does the same, small portion of the work themselves and delegate it. And the final friend can't make the problem smaller, just makes a layer of cake, gives it back to the friend who asked to make it. That friend puts the layers together, gives it back to the friend who asked it. That friend puts the 3 layers together, gives it back to me, and I take the 3 layers and put them back together, and now I have the 4-layer cake. This is how the automagic part is working internally. I keep making the problem smaller and smaller and smaller, delegating. When I hit a base case, I can start returning my value and putting the results slowly together. As a result of this, we will talk about the following 2 scenarios. In recursion, we're going to have one base case, at least one or multiple base cases, and one recursive case or more recursive cases. The base case is going to be the scenario where I am reaching the bottom line and I can't make the problem smaller and I can solve immediately without delegating, right? So that's what's going to be our base case or base cases. It's a very simple case I can immediately solve without making the problem smaller. This will make it so that we stop, right, our delegation work. Once we hit the base case, we're done, we keep returning. The recursive case are cases where I'm making the problem smaller, delegating, getting the result, and combining. Making the problem smaller, delegating, getting the result, and combining. And by smaller, I can mean multiple things, right? Making a list shorter on a dynamic array or an array, making it shorter. Making a number smaller, right? Making a problem simpler. So anything that leads me to that base case, right? So that I can stop at the base case and return. In the scenario with the cake, the base case is when we have the 1-layer cake, we can just return it. The recursive case is all the other scenarios, right? When I'm making smaller delegating, right? Getting the result from the previous call, combining, getting the result from the previous call, combining, getting the result from the previous call, combining, right? So these are the recursive cases. This is the base case. So to review, in a nutshell, a recursive problem is one that is calling itself over and over again. How can we determine that we stop? 1, we make the problem smaller. 2, we delegate it. 3, once we hit the base case, we return and combine the problems as we go up. A base case is a case that can be solved immediately. We don't need to do extra work. A recursive case is a case where we're making the problem smaller or shorter or simpler and so on and so forth. You will ask, how does this look like in code? Well, let's take a look at pseudocode first. Pseudocode is just code that doesn't belong to a specific programming language. More, it's trying to determine how the algorithm is going to look like. And then I'm going to show you specifically how we do it in C++ and Python. So in this case, as we said, every recursive problem needs to have a base case, right? This is where we end something. And a recursive case, this is where we make smaller, delegate, combine, make smaller, delegate, combine, right? Let's say I'm going to call my function recursive function that is getting some problem. This can be anything, making a cake, we're going to see summing the elements in an array, finding factorial, right? Whatever problem it is. I can call my function whatever I like, recursive function, my function, make cake function, whatever it is, right? What is the base case? Some scenario where the problem becomes small enough that I can immediately solve it, right? So it's a scenario that we say, if this problem has reached some very small, simple level, and I can just go ahead and solve it and return, that's my base case, right? So in this case would be, if the layers of cake that I'm asked to make are 1, I just make the layer of cake, right? What about the recursive case? The recursive case is going to have the 3 portions that we talked about. First, I need to make the problem smaller, right? So in the cake example, I'm subtracting 1 layer and asking somebody else to do it. Once I make the problem smaller, I have to call myself recursively with a smaller problem, right? So I'm going to call recursive function, which is the name of my function here, with the smaller problem. This is the same as I have 4 layers. I ask my friend to do 3 layers. That friend asks the other friend to do 2 layers. That friend asks the other friend to do 1 layer, right? So the asking is calling myself recursively to make cake, right? That is going to give me a smaller result, right? In the case of the 2-layer cake, I get a smaller result of 1. In the case of 3-layer cake, I get the smaller result of 2 cakes. In the case of 4-layer cake, I get the smaller result of 3 cakes. And the only thing left for me to do is combine it with whatever was left over, right? So in the cake example, again, I get the 3. I put it together with a 4. So every recursive problem will have a base case and a recursive case. We may have multiple base cases, as we will see today. We may have multiple recursive cases, but we need at least one. The base case is when my problem becomes so small that I can immediately solve it. I can immediately answer the question that I have. The recursive case has 3 parts. Part 1, I have to make the problem smaller. Part 2, I have to call myself recursively with a smaller problem. So I call the function recursively. Part 3, whatever gets returned from the smaller result, I somehow combine it with what was left of my previous problem. Having seen this high-level theoretical example, as well as the code or the pseudocode of recursion, let's go ahead and look at some concrete examples of how we can use recursion, particularly in math, right? So you may be familiar with factorial, and factorial is one of those concepts that is recursive. For example, if I'm trying to figure out what 5 factorial is, it's 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. Right? If I wanted to figure out what 6 factorial is, obviously I can do 6 multiplied by 5, 4, 3, 2, 1, or I can do 6 multiplied by 5 factorial. So this is an example of recursion. If I'm trying to calculate 6 factorial, what I do is I ask a friend to calculate 5 factorial, they get me back the number, and I multiply it by 6, and I have the result in factorial. So factorial is recursive. More in general, we can say that x factorial is x multiplied by x minus 1 factorial. Okay, this is beautiful because based on this definition, now we can go ahead and figure out what our base case and recursive case are. Let's look at the base case. What's the base case? When my factorial becomes 1, I can immediately calculate it. I know 1 factorial is 1. You may say, well, we could use 2, right? 2 factorial is also 1. Sure. Either 1 or 2 or even 0. 0 factorial is also 1. So any of those cases where I can immediately answer the problem, it's a base case. In this case, I'm just going to choose x equals to 1 because we know immediately that 1 factorial is 1, so we can solve that problem without doing any calculations. How can I make the problem smaller? Again, we said to calculate 6 factorial, I will ask a friend to do 5 factorial, right? To ask 5 factorial, they're going to ask their friend to do 4 factorial, and so on and so forth. So the recursive case, making the problem smaller would be x minus 1. I'm making it 1 smaller. And then I will call myself recursively with this x minus 1. And when I get the smaller result back, what do? I have to multiply it with the value x, that is what's left of the problem. What do I mean by that? When I was trying to calculate 6 factorial, I asked my friend to calculate 5 factorial, right? They calculate 5 factorial for me, they give it back to me, and then what's left of me to do? I have to multiply the value that they gave me by 6, right? And 6 is the x that I was looking for. So, base case, when x is equal to 1, a recursive case, I make the problem smaller by 1, and then whatever that result gives me, I multiply it by x. Let's take the code, the pseudocode that I showed you in the previous slide, and let's try to fill in here each of those portions of factorial, right? When you're writing recursive problems in general, you want to take this code as a basis, and you want to think about what is my base case and what is my recursive case. For recursion, it's not so much about writing the code about it, but thinking how to break down the problem into one or more base cases and one or more recursive cases. So we said, I'm going to have my recursive function here. What is my problem? I'm trying to calculate x factorial, right? What is my base case? If my x becomes equal to 1, that's my base case. What do I return then? I return 1, because 1 factorial is actually 1. How can I make the problem smaller? I take x and subtract 1 from it, so that's x minus 1. I will call myself recursively with the smaller problem, right? And this is going to give me the smaller result. And then what do? I go ahead and take my x and multiply it by the smaller result. Okay, so again, I take my pseudocode, I think what's my problem? I'm trying to calculate x factorial. When do I stop? When x is 1, I return 1. How do I make the problem smaller? X minus 1. I call myself recursively with a smaller problem, I get the smaller result, and how do I combine it? I go ahead and multiply it by x. I strongly encourage you to memorize or store in an index card this pseudocode, because this is going to be extremely valuable as you're working with recursion. Every recursive function will have the same structure. A base case, where it's the smallest we can get the value, and then we return immediately. A recursive case, where we're making the problem smaller. We call it recursively. As you notice, this part didn't change. I would only need to change the functioning here if I'm calling it differently. And then combining the smaller result with what was left of the problem, in this case, my x. Okay. Let's take a look how we would write this in C++ and how we would write it also in Python. So I'm going to quickly move to VS Code. I'm going to go over here. You already have the solution for factorial right here, but I'm going to go ahead and delete it so we can write it together. And this would be a good practice exercise for you as well to follow along in writing the factorial function. So my factorial is going to return an integer. I will call it factorial, and my problem is x. I'm trying to calculate x factorial. What did we say? I need a base case, right? And I need a recursive case. What is my base case? Well, based on the pseudocode that I had on the previous page right here, my base case is going to be if my specific value x reaches 1, right? This is my base case. I cannot make x smaller. I will go ahead and return 1, because 1 factorial is 1. Otherwise, if I'm not in the base case, what do? I have 3 steps I need to do. Step number 1, right? I have to make the problem smaller. How do I make it smaller? I subtract 1 from x. 2, I have to call myself recursively, right? So I'm going to call this factorial that I wrote recursively with a smaller problem, right? This is the delegation part. You're calling your friend, who's calling their friend, who's calling their friend, who's calling their friend. This is going to return for me a result. Okay. The only thing left for me to do, so this was step 2, right? Call recursively and get the smaller result. Step 3, now I have to go ahead and combine. How do I combine it? I take my x value that is waiting for me, and I multiply it with the smaller result. Okay, and tada, I have my recursive solution of the problem. Again, this is following the pseudocode from before. It's not necessarily so hard writing the code in C++ or Python. It's a little bit more challenging to figure out what your base case is and what your recursive case is. I will give you a minute to think how we can implement factorial in Python. Pause the video, go ahead and do it on your own, and then let's come back together and solve it in Python. Okay, let's give it a try to write factorial in Python. So I'm going to go over here. I am going to delete the current implementation and then implement it from scratch together. I'm going to define a function. I'll call it factorial. I can call this whatever I want. My factorial, this factorial, lecture factorial, it doesn't matter. As usual, we are going to have a base case and we're going to have a recursive case. What is my base case? When my x becomes 1, apologies for the typo, this is my base case, I'm going to return 1 because 1 factorial is 1. Otherwise, I'm in the recursive case. I have to do 3 things. Number 1, I make the problem smaller. Number 2, I call myself recursively, right, with this smaller problem. From that, I get a smaller result, right? And the only thing that is left for me to do is multiplying the smaller result with x, and I get the result, right? So let's actually save this and run it to see if we have any errors. So I'm getting a factorial of 5, 120, right? If I call factorial of 7, that should give me the value of 7 factorial, which is in this case 5040. Okay. You'll say, how is this working internally? Because, okay, it makes sense that we think about the base case and the recursive case, just like we have it here. We write the pseudocode, and then we translate it into C++ and Python. But how is this happening internally, right? So what I want us to do is code trace this together. It doesn't matter if you're doing the code tracing in C++ or Python. Both are going to work equally. So I'm going to do the Python, provided we are at this page. Let's say somewhere down here, you're calling factorial, right? And apologies for writing this, factorial of 5, okay? So I'm trying to identify what 5 factorial actually is. What is happening is that I don't know what 5 factorial is, so I'm going to put a bookmark here and say, hey, wait for me while I go calculate, oops, apologies, let's go back. While I go calculate factorial of 5. I check, is 5 equal to 1? No, it's not. So I'm going to go and call myself recursively with a smaller problem. I'm going to do 5 minus 1, 4. And I'm going to call myself recursively with 5 minus 1, which is 4. Okay? Do I know what factorial of 4 is? I don't, right? So I need to go and actually solve this problem. So factorial of 5 is internally calling factorial of 4. Right? So I'm going to change colors to represent this. I'm going to put another bookmark here and say, hey, wait for me here while I will go and calculate factorial of 4. I check, is 4 equal to 9? No, it's not. I go ahead and make 4 minus 1 gives me 3. So that's my smaller problem. I call factorial with 3. Do I know what factorial of 3 is? No, I don't. So again, I'm going to change colors, put a little bookmark here and say, hey, please go ahead and calculate for me factorial of 3. Okay. So I go ahead, call factorial of 3. And I check, is 3 equal to 1? No, it's not. So I'm going to go ahead and make the problem smaller. 3 minus 1 gives me 2. I'm going to call factorial of 2. Do I know what factorial of 2 is? No, I don't. So again, you get the gist of it now. I put a bookmark here and I say, go ahead and calculate factorial of 2. I'm going to check is 2 equal to 1? No, it's not. So I'm going to do 2 minus 1 gives me 1. I will call myself with factorial of 1. Okay. So here, apologies, I forgot to write factorial of 2, right? So now, this is the final step. I'm calling myself with factorial of 1, right? Do I know what factorial of 1 is? No, I have to go calculate it. Okay, so I will go here, calculate factorial of 1. Okay, and I'll say, okay, is 1 equal to 1? Yes, it is. Is 1 equal to 1? Yes, it is. We finally hit the base case. We don't need to make the problem smaller anymore. I'm going to return 1. Where do I return this 1 to? I return to the problem who called me. Who called me over here, right? So I have to come back and return this 1 here. Who called me? Factorial of 2, right? Factorial of 2 called me and said, hey, you go ahead and calculate what factorial of 1 is. So I return to factorial of 2 the return value 1. What does factorial of 2 do? Well, now it knows, right? The factorial of 1 is actually 1. So let me change the colors to go to orange because orange was factorial of 1, right? So this is 1. Okay? So it goes ahead and multiplies this 2 with 1 and returns 2. Who does it return the 2 to? The function that called it. Remember? We said wait for me here while I calculate factorial of 2, right? So I will return 2 to who called me, which was factorial of 3, right? So factorial of 3, now it knows that factorial of 2, right? This call here with 2, this one is actually 2. And it's going to take the value 3, right? And multiply with 2, and it's going to get 6. So factorial of 3 is going to return 6. Who does it return it to? It returns it to the call factorial of 4 who's waiting for me. So over here, I'm going to go ahead. Factorial of 3, right, is going to be 6. I take the smaller result and multiply it by 4. So 4 multiplied by 6 will give me 20. So I am returning 20 from the call of factorial of 4, right? Where is this 20 getting returned? To the function that called me originally, right? Over here. So here I have 20, and I'm going to go ahead and multiply 5 with 120, sorry, with 20, which is going to give me, sorry, I did the math wrong here. 6 multiplied by 4 is 24, and 5 multiplied by 4 is 120. Anyways, the math is not important. It's sort of the process that we're going through, right? So factorial of 5 multiplies 5 with the result that we got from factorial of 4, which is 24, and that it returns the final value, okay? So all these calls are happening internally. The stack of the computer, which we talked a little bit about in the dynamic array lecture, the stack is keeping track of each of these individual calls, right? When the first call is being made, right? When the first call 5 is being made, it keeps in mind that the value of x is 5, and it's waiting, right, for factorial of 4 to return its value. Factorial of 4 does the same thing. It remembers that in this instance, x is 4, and it calls factorial of 3. Factorial of 3 does the same thing. Factorial of 2 does the same thing. Factorial of 1 does the same thing. X is equal to 1. Whenever we hit the base case and we return, we give the value to the person that immediately called me. Remember with the cake example, if I have 4 layers and I ask somebody to give 3 and they ask somebody to give 2, the person who makes the 2 layers doesn't give it to me, it gives it to the person who called them, the person who had 3 layers and said, hey, you friend of mine, do 2 layers for me, right? And I receive what the person with 3 layers gives me. So the person who calls you, that's who you owe an answer to, okay? So factorial of 1 gives factorial of 2, 1. Here we said x was equal to 2, we multiply 2 by 1, we return 2. X here is 3, we multiply 3 by 2 gives us 6. 6 and 4, 24, and then 24 and 5, 100. Okay? So this is all being kept track of by the stack of the computer. We don't need to do this. The computer, Python, C++ is doing it itself via the stack, and we'll learn about the stack data structure a little bit later in the module. It's keeping track of each of the variables for the function, the individual function calls, right? And then once it receives a value from the previous function call, it can do the combination and return it back. You don't need to be able to do this, right? When we're writing recursive code, the part that we care about is this, the pseudocode filling in the portions. However, it is very helpful to understand how recursion is working internally, both to figure out when you run into bugs, how to fix them, but also to be able to trace code like this. And we're going to see a couple more examples of this today. So, just to review, we talked about recursion as a concept where we're making a problem smaller, delegating it, and then getting the smaller result and combining it together. We saw how to write pseudocode for recursive problems where we identify first what's our base case, that we can solve the problem immediately without making it smaller. What's our recursive case? How do we make the problem smaller? Call ourselves recursively, and then combine that smaller result with what's left of the problem. We saw how factorial is recursive and how we can implement it both in Python and C++. And we did a little bit of code tracing with factorial in Python. It would work the same way with C++. Let's look at the second example. Fibonacci numbers, again, from the math domain. They are recursive. If you're familiar with Fibonacci numbers, Fibonacci of 0 is 0, Fibonacci of 1 is 1. And for every number after that, Fibonacci of a given number, for example, Fibonacci of 5 is equal to Fibonacci of 4 plus Fibonacci of 3. As you can see, this very easily breaks up into the base case. Once we hit 0 or we hit 1, I can return 0 and 1 immediately. Otherwise, I will make the problem 1 smaller and 2 smaller, and then combine the results of each of those smaller problems together. Note, this is an example where we have 2 base cases and 2 recursive cases. As we said, we need to have at least 1, but we can have 2 or more depending on the scenario. Knowing this definition of a base case and a recursive case, I want you to go back to the pseudocode that we had for the very first time here. Okay, this pseudocode, and try to fill in here the base cases and the recursive cases. Okay, so based on this and the explanation of Fibonacci, take a minute, pause the video, and try to fill in on your own what the base case and recursive cases is going to be. Okay, now that we're back, let's take a look at the actual code, right? We are going to try to calculate Fibonacci of n, and this is in C++, but again, same thing in Python, same thing in Java and other languages. We're trying to calculate Fibonacci of n. What is my base case is going to be? If my n becomes 0 or my n becomes 1, I'm going to return 0 or 1. Obviously, you can break this up into 2 if conditions. If n is 0, return 0. If n is 1, return 1. But either way, I have combined this here with the OR operator. Otherwise, what's my recursive case? I make the problem smaller, but I'm making it smaller twice now. I make it smaller once, I make it smaller a second time, and then I get that smaller result from once, I get the smaller result from second time, I combine them together and return that value. This is how the base cases and the recursive cases are going to look for Fibonacci C++. Let's go ahead and implement this together in C++. So over here, I have the solution, but I'm going to delete it. I'm going to call my function fib or Fibonacci, it doesn't matter. It's going to take a value n. And again, I'm thinking, what is my base case and what is my recursive case? In base case, we said that if my value n is 0, right, or if my value n is 1, and again, I can split this, I'm going to return either 0 or 1, depending on the scenario. Otherwise, I have my recursive case. Obviously, this I can break down into a smaller problem 1, right? This is n minus 1. I can have smaller problem 2. This is n minus 2, right? And then I can have smaller result 1, where I call Fibonacci with n minus 1. And then I can have smaller result 2, where I call Fibonacci with n minus 2. And n minus 1 is smaller problem 1. Let me spell this correctly. Okay. So this n minus 1 is smaller problem 1. This n minus 2 is smaller problem 2. And then what I do is I combine the solution smaller result 1 plus smaller result 2. Right? So I can totally write it like this. I make the problem smaller. I call myself recursively with a smaller problem. Oops, and I meant to say here I put smaller problem 1, here I put smaller problem 2. And then once I get those two results, I combine them together, right? Or the easy way, we can take this whole thing and smush it into one statement, whichever way works better for you, right? So I can take that whole thing and basically say return the call of Fibonacci n minus 1 plus Fibonacci n minus 2, right? So this whole code over here is equivalent to this one. Okay. We saw how Fibonacci is a recursive function. We also saw how to write it in C++ recursively. I want to give you a minute to write it in Python. So pause the video and come back to it once you have this algorithm for Fibonacci written in Python. Let's go ahead and type it in Python together. I'm going to go ahead and delete my current implementation. Again, as I said, the implementation itself is not necessarily challenging. It's a little bit more challenging being able to break down the problem into base cases and recursive cases. So I'm going to have my Fibonacci, which is equal to n here. I'm going to say, hey, if my n is 0 or if my n is 1, I'm going to return n, right? If you wanted to make this a little bit more broken down, you can say if n is 0, I'm going to return 0. Otherwise, if n is 1, I'm going to return 1, right? Otherwise, this is my recursive case, right? I need to go ahead and return Fibonacci of n minus 1 plus Fibonacci of n minus 2, right? So I could break it down with smaller problems, smaller result, or I could write it in one line as follows. That, in a nutshell, is how Fibonacci works and how we implement it both in C++ and in Python. Let's figure out how these Fibonacci calls, right, are happening behind the scene. We saw with factorial. The factorial of 5 calls factorial 4, which calls factorial of 3, which calls factorial of 2, which calls factorial of 1. And once we hit that base case, we can start returning. How does it work when we have two calls, n minus 1 and n minus 2? Here's what's happening internally. There's going to be, again, some way of keeping track by the stack of the computer of the function calls. So let's say I'm going to call Fibonacci of 4, right? Fibonacci of 4 is going to first call Fibonacci of 3, right? And I have to wait. I can't call Fibonacci of 2 yet because I need to finish figuring out what this value is before I go call Fibonacci of 2, right? So Fibonacci of 3 goes ahead, calls the function again, is calling Fibonacci of 2. It's not calling Fibonacci of 1 yet, right? Because I need to finish what Fibonacci of 2 is. Fibonacci of 2 goes ahead, calls itself recursively again, calling Fibonacci of 1. Doesn't call Fibonacci of 0 yet, right? Because we need to figure out what Fibonacci of 1 is. Once it calls with Fibonacci of 1, right? Now we can finally return the value 1. So Fibonacci of 1 is 1. I'm done with the first part of this Fibonacci call. Right? But Fibonacci of 2 called 2 minus 1, which is 1, and 2 minus 2, which is 0. So now I need to go ahead and calculate what Fibonacci of 0 is. So I go ahead and make that call. Fibonacci of 0 is going to give me 0. So finally, for Fibonacci of 2, I have 1. Right? For 2 minus 1, I have 0. For 2 minus 2, 1 plus 0 is going to give me 1. Right? So I'm combining them together. Finally, we know that Fibonacci of 2 now is 1. Let's switch colors a little bit so we can see what Fibonacci of 3 is doing. Fibonacci of 3 called 3 minus 1 Fibonacci of 2. Now it has to go ahead and call 3 minus 2, which is Fibonacci of 1. We don't know what Fibonacci of 1 is, so we're going to go ahead, calculate it. Turns out it's 1. So I have Fibonacci of 2, which gives me 1, and Fibonacci of 1, which also gives me 1. So 1 plus 1 is equal to 2. So finally, Fibonacci of 3 is equal to 2. Can I give the answer for Fibonacci of 4 already? No, I can't do that yet because Fibonacci of 4 just finished this first portion, 4 minus 1, right? So we figure Fibonacci of 3 is equal to 2. I have to go and figure out what Fibonacci of 2 is, right? So it's going to repeat again. I call Fibonacci of 2, which calls Fibonacci of 1, which returns 1. Fibonacci of 2 is going to call Fibonacci of 2 minus 2, which is 0, which is going to return 0. 1 plus 0 is going to give me 1. And finally, now I know that Fibonacci of 2 is 1. 2 plus 1 is going to give me 3, and I have the answer for Fibonacci of 3, for Fibonacci of 4 being equal to 3. So this is what is happening behind the scenes, right? Fibonacci of 4 calls 3, which calls 2, which calls 1. Once that comes back, Fibonacci of 2 has to call 0, that comes back, right? And we keep repeating. Again, we don't need to keep track of this. The computer in Python and C++ automatically does it for you. We need to be aware how these function calls work like and how we can trace them. This is called a recursive call tree because it has the structure of a tree with nodes, but you should be aware of how to trace this step by step. Okay, so we saw examples of factorial, which has one base case, one recursive case. Examples of Fibonacci, which has more than one, two base cases, two recursive cases. All of these examples were with numbers. So let's look at a recursion version with data structures that we've seen so far, right? Particularly, I will use dynamic arrays because they're a little bit easier, but you can apply the same logic to fixed size arrays. So we will work quite a bit with arrays and recursion, especially with search algorithms and sort algorithms. They rely on recursion. They make the solution look much more elegant. Today, we will practice with a simple example of how I can add elements to an array. I'm also going to demonstrate for you how I would solve this problem if it was given to me and how I would like you to solve this problem. I don't want you to jump directly into code that can make things a little bit more complicated. Instead, I want you to focus on that pseudocode that I showed earlier in the lecture and the following questions. Identify what the base case is. Identify how to make the problem smaller. Identify what the recursive case is, and identify how to combine the results together. So you should think on a piece of paper about those options anytime that you're trying to solve a recursive problem. So I'm going to solve this problem. I have given you a little chart here, but I kind of want to do this chart together with you so that you can follow along and figure out what we're doing here. So I am trying to recursively add the elements. Whoops. Let me do something very quick. Let me copy this and I want to share it with you on a new page. Okay, so let's go ahead and put this here. Okay, so I want to recursively solve the problem where I am adding the elements of a dynamic array, right? So I'm trying to add the elements of a dynamic array. In this case, what I always advise you to do is to take a very simple example, let's say with 4 elements. So I want to recursively add these elements, right? If I were to do it with a for loop, iteratively, or with a while loop, I do 1 plus 2 plus 3 plus 4 and have the result, but I'm trying to use delegation. So how can I make the problem smaller, right? I'm going to keep one element to myself, right? Just like we did with the cake. Keep one element, one layer to myself, and then delegate and ask a friend, hey, you figure out how 2, 3, and 4 work for me, right? So what's the sum of 2, 3, and 4? Again, same thing as the cake example. I'm taking a problem, making it smaller. So to answer my question 2, how do I make the problem smaller? I keep an element to myself, and then I give the rest of the elements in the list to my friends. To do this in programming, we can use something like list slicing, or we can keep an index where we are in the list. That's, again, not important. We need to figure out first how the pseudocode is going to look like. Okay. What is my base case, though, in this scenario? I don't know yet. So let's continue with this example. I'm going to keep 2 to myself, or my friend keeps 2 to themselves, and then they're going to call recursively with 3 and 4. Okay. Their friend is going to keep 3 to themselves and is going to go ahead and ask another friend to calculate 4. Right? And that friend is going to keep 4 to themselves and is going to ask themselves, or another friend of theirs, to calculate what the empty list is, right? What is the sum of the elements in an empty list? And again, I'm using the term list or array, dynamic array interchangeably here. Can I make the array smaller in this scenario? No, I can't. This is the smallest that the array could be. I cannot make an array smaller than 1. So that is going to be my base case, right? So once I hit that base case, right, this is when I can solve the problem immediately. What's the sum of the elements in an empty array or in an empty list? The sum of the elements is 0. Okay, so this is going to be my base case. And I have successfully answered the first two questions. How do I make the problem smaller? By keeping one element to myself and giving the rest, delegating it recursively. And what is the smallest problem that I can reach? This is my base case. Right? So you can imagine when you write the function, this is going to be something along the lines of if the list is empty, I'm going to return 0 because the sum of the elements is 0. Okay. Now, what do I do in the recursive case, right? Well, in the recursive case, I went ahead and made the problem smaller, right? Which means that that is going to give me a smaller result, right? So this 0 is going to be passed to 4. That is going to be passed to the other one, be passed to the other one, be passed to the other one, right? So effectively, by identifying how to make the problem smaller, I have also identified what my recursive case is. Now that I have this 0, this is going to be returned over and over again. How do I combine the results, right? The best thing to do in this scenario is the following. Forget about these steps, right? For a second, let's forget about all these steps. And let's assume that your friend is going to give you a correct result. So 4 plus 3 equals 7 plus 2 equals 9. So let's assume that your friend magically will give you this 9, right? How do you combine it with what's left of your problem? So the one that is left of your problem, how do you combine it? You do 1 plus 9. Right? And then you're done. You found the sum of the elements in the list. That's 10. Right? That is the fourth and final portion of recursion, the combination of the results, right? So you identify what your friend is going to give you. Again, assume that the friend magically is going to give you this value. And once they give you that value, you combine it with what was left of your problem, which was this one, and that gives you the answer 10. So I'd like you, whenever you're solving a recursive problem, to use a little example like this one with 3 or 4 elements. Identify how to make the problem smaller. Hit the base case. Once you have the base case, you know what to return. You also know what the recursive case is because you already called yourself with a smaller problem. And then to identify how to combine the portions, forget about this bottom part of the exercise. Think about this is you and this is your immediate friend. What is your immediate friend going to give you, right? The correct answer. Assume that magically your friend knows the correct answer. Combine that with what is left of your problem. Okay? So let's take a look at this, how this is going to be in pseudocode, and then I am going to write it for you in Python, and I leave as an exercise for you to write it in C++ yourself. So let's go ahead, and I am, again, using pseudocode for now. I'm going to define some function. It doesn't matter what I use, and the function is going to be called recursive list or something, or recursive array, depending on the programming language we're at. I'm using lists in this case because we said that the dynamic array implementation of Python dynamic arrays is lists. So this is going to take my list as an element, right? What is the first thing that I do in the code? I have to think about my base case, right? So my base case will say something along the lines of if my list is empty, right? Or if the size of elements is 0, depending on how you want to implement it is totally fine, right? So when I have 0 elements or my list is empty, I know immediately what the sum is, right? I'm going to return 0. So this base case, I translate it over here. If my list is empty, I return 0. What about the recursive case, right? Well, in this scenario, I have to make the problem smaller. Right? So here I'm going to have smaller problem, right? What's the smaller problem? I need to make the list smaller by 1. I can use an operation like list slicing, right? So that is going to make my list 1 smaller. Slicing is an operation very common in multiple programming languages that allows you to take all the subsection of a list. So what this is saying is take all the elements of the list, but the first one. Right? Take all the elements of the list, but the first one. Take all the elements of the list, but the first one. Take all the elements of the list, but the first one. Then what do? I go ahead and call myself recursively, right? So I will use the function name recursive list over here, right? And I'll call myself with a smaller problem. This is the delegation. And this is going to give you a smaller result. What do you do with that smaller result? This is the final portion. You have to combine it. How did you combine it? So this is the smaller result the friend gave you. You have to combine it with what was left of you. In this case, the 0th element of the list. So what you're going to do over here, you're going to return, okay, the smaller result plus list of 0, right? Which is the 0th element of the list, which you kept to yourself. Because when you made the problem smaller, you gave your friend a smaller problem, but you kept the list of 0 to yourself, right? So this first question is being answered here, right? That's the base case. This is how I make the problem smaller. This is the recursive case. And then finally, this is the combination step. This is also the reason why I strongly encourage you, when you're solving a recursive problem, to take a little example like this in order to answer these questions, which directly translates to the parts of the pseudocode over here. You need to figure out a little example what the base case is, how to make the problem smaller, and once your friend, your immediate friend, gives you the result, how do you combine it? It could be plussing together, it could be multiplying, and so on and so forth. Okay. Let's look at this pseudocode now in Python, right? Let's go over here. If my list is empty base case, I'm going to return 0. I make the problem smaller, call myself recursively with a smaller problem. I'm going to return the sum of those two elements together. Okay. What I would suggest you do after the lecture, you close the slides and you try to re-implement this from scratch. Make the little example, right? Have your 4 questions next to you. You don't need to memorize them, but have them close to you. Do the little example of breaking down the problem, get the return value, pull it back together, and then write the pseudocode. Translate that little example into pseudocode, and once you have the pseudocode, write it in Python. I will also leave as an exercise to you to write a sum of lists in C++. Once you have it in Python, it should be relatively easy to convert to C++. You can use here either the dynamic array implementation that we did together, but I would suggest it would be easier to use the standard vector, which is the C++ implementation of a dynamic array. If you Google standard vector, you will be able to see how to make the slicing of the array, right? This is how we do it in Python, that we slice it by keeping one element to ourselves and the rest goes to the recursive function call. Standard vector also has a functionality like that. Once you have an answer, come back to the code that we have over here, right? Test your code in Python, test your code. I have it down here in C++, and I have included a bunch of test functions as well that you can see is your function recursively working correctly and giving you the correct answer. So in a nutshell, today we covered quite a bit of ground with recursion. We introduced what recursion is as an idea. We introduced the steps of the recursion, make the problem smaller, delegate, combine the smaller answer. We saw an example of recursion with cake. We introduced what the base case is, a problem that can be solved immediately and cannot be made smaller, and the recursive case, which is calling yourself with a smaller problem, getting the result and combining, right? A problem that you need to make smaller. We saw a bunch of exercises, factorial, where we have only one base case and recursive case. We saw Fibonacci, we have 2 base cases, recursive cases, and we saw an example with lists when we're trying to sum the elements of a list. When you're solving a recursive problem, always on a piece of paper, identify your base case, how to make the problem smaller, how to call yourself recursively, and how to combine the result based on the examples that we did. We also talked a little bit about how to trace the code, both for factorial and for Fibonacci. That is something that the computer does automatically for you. You don't have to worry about doing it, but you should be aware of how the calls are made so that you can identify different bugs that you have in your code. I hope you found this lecture a lot of fun. Recursion is a very beautiful, elegant way of thinking, and we're going to see it more and more in the upcoming lectures. Thank you, and I'll see you in the next lecture.